Hello, everybody. So, welcome to the first video of the quarter covering content. This video covers section 1.1. I believe it's called Introduction to Functions in the textbook, or another way I'm going to rephrase it is through a question: what is a function? And I want you to notice that I'm going to be going through a section 1.1 handout, and you can find a PDF. You can find a copy of this PDF in the same section that you used to find the video link. Okay, so first, what is a function? I can't really talk about a function without talking about what a relation is. And look at this first definition here. Really, the basic idea is a function is some method or some process by which one quantity is converted into another quantity, or any object or element really is converted into any other object or element. And a relation is, I guess, a less strict restriction than a function. Okay, well, we'll see what a function is in just a second, but you can't talk about what a function is without talking about what a relation is. A function is really just a special kind of relation. And it says below, if you read this, a relation is the pairing of elements, and again, most of the time for us, these are just going to be numbers. So it's the pairing from one set of numbers, okay, with the elements, again, numbers from another set. Okay, so you have two sets of numbers. A relationship is any way of creating pairs of elements from each of the two sets. Okay, there's no other requirements. I would take one element in the first set, and then I just have to choose what I'm going to pair it with from the second set. Okay, now for an example, just a simple relation would be basically thinking about the conversion between the temperature in Celsius and the temperature in Fahrenheit. So below here I have a table, and it gives you a relation, or you can think relationship between the temperature in degrees Celsius and the temperature in degrees Fahrenheit. Okay, so one thing you notice is that, let me switch colors. There's a blue. You'll notice, okay, I just boxed, when the temperature in Celsius is 0 degrees, the corresponding temperature in Fahrenheit is 32 degrees. So that is a single pairing in this relationship, or relation, between Celsius and Fahrenheit. Okay, 0 degrees Celsius corresponds to 32 degrees Fahrenheit. Okay, or when the temperature is 1 degree Celsius, it's related to the temperature of 33.8 degrees Fahrenheit. Okay, and this is just 4 different pairings in that relation. There actually is, okay, we're going to see in a second, one way to describe a relation is just to list the elements in both sets, and if they're in the same row, then they would be paired together. Again, so if you look down here in the third row, okay, this is a pairing of 2 elements from each set in this relation. So when the temperature is 2 degrees Celsius, okay, the temperature in Fahrenheit is 35.6. Okay, and again, a relation is any way of taking numbers from 2 different sets and pairing them together, and there's no rules other than numbers are paired between the sets. Okay. Okay, now one way to describe a relation is to just by literally saying what element in the first set gets paired with what element in the second set. Now, for this particular relation, or relationship between Celsius and Fahrenheit, there is an equation that does allow you to convert. So again, one more time, relations or functions can be expressed through tables, equations, graphs, or verbal descriptions. Okay, so at the bottom of a page, or more specifically, you can talk about a special kind of relation called a function. Okay, and again, in the previous example, the relationship between Celsius and Fahrenheit is a function, turns out. So read the definition carefully. It says a function is a relation between two sets, assigning to each element in the first set exactly one element in the second set. Okay. Again, so it's just a rule. Okay. It tells you how to pair elements from one set to another. Okay. But be careful, because there's a specific requirement that it assigns each element in the first set, and then the important statement here is exactly one element in the second set. So in the previous example, when you're thinking about Celsius to Fahrenheit conversions, right, think about assigning a Fahrenheit temperature to a Celsius temperature. For each Celsius temperature, it only makes sense to assign it to one and only one Fahrenheit temperature. Right? That wouldn't make sense to have one single Celsius temperature correspond to more than one temperature in Fahrenheit. Okay, so it's a very special, a function is a special type of relation where each number in the first set can only be assigned to exactly one number in the second set. Okay, the first set, which is called the set of inputs, is also named the domain of the function. And the second set, called the set of outputs, is called the range of the function. And the independent variable is the variable associated with the domain. Okay. So anything in the domain, or the variable that corresponds or represents elements in the domain or set of inputs, is called the independent variable. Usually it's x that we use, but you can use any letter you like. The dependent variable is the variable associated with the range. Okay, so if usually the letter chosen for the dependent variable is y, okay, that letter represents anything that could take place or come from the range. Okay, that's what we mean by the dependent variable. It's the variable that represents the outputs. The independent variable is the variable that represents the inputs. And when we do have a function, make sure you read this note on the bottom. When we do have a function, we say that the output is a function of the input. Okay. Okay. So just to understand the idea of the definition of a function, I have two tables below in example 3, and this should be example 2, but I must have missed an example somewhere, deleted an example. So, but what I have here is I have two tables, and each table represents a relation. Okay, so I'll box this one on the left. That's relation 1. Here's relation 2. And the question is, could each of these relations below represent functions or not? And if so, it says find the domain and relation. It says find the domain and range. Okay. So the idea here is that you want to make sure that each input is assigned one and only one unique output. And in terms of looking at tables or relations representing tables, you want to make sure essentially that if the input is ever repeated more than once, you want to make sure that you don't have two different outputs. So if you look at the first relation, you'll notice that when one of the relations or pairings is that when the input is 2, for that particular input the output is 1. But you'll notice down at the bottom that there is another pairing with an input of 2, but this time the output is 7. Okay, so what I'll say here is that relation 1 is not a function, since 2 has two different outputs. Okay. namely it has the outputs of 1 and 7. So relation 1 is not a function. We have found an input that is being assigned to multiple outputs. Now relation 2, if you look at the inputs that you have on the left, okay, you're going to notice that no input repeats itself. Okay, and just for example, even if one did, if I had -5 and the output was still 20, okay, actually let me clear all strokes for just 1 second. Okay, so I'm focusing on this relation. So just for example, as written, you see that I have all unique inputs. None of those inputs are repeating, and I could add a -5 with an output of 20. So, you know, even if I did have a repeating input, I want you to notice that both of those pairings still have the same output. Okay, so when you look at one of these tables or one of these relations, as long as the inputs do not repeat, it will automatically be a function. Okay, because each input technically only appears once and has only one output. Okay, even if an input was repeated, if the output is not different, it would still be a function. Okay, so relation 2 is a function. Okay, since each input is assigned only one output. Okay. Alright, and so relation 1, not a function. The input 2 has multiple outputs, or outputs of 1 and 7. Second relation, okay, second table, does represent a function. Each input only appears once and is assigned to only one output. Now, since the second relation is a function, I can go ahead and find the domain and the range, which I'll just represent by D and R. And we're going to see more of this later. Domains can be represented in a lot of different ways. They can be represented in set notation. They can be represented in interval notation. And the interval notation would only be used if you had like an infinite range of values, like all numbers between, say, -5 and 7. But in the case of this function, there's only a finite number of inputs. So what I would do for the domain is I would just list these. So I'd have -5, -3's in the domain, 0, 2, 4, 5, 7. Okay, there's my domain. And the range is just a set of outputs. And again, this function does not necessarily have a formula or an equation or any seeming rule to how the outputs are found from the inputs. They're just listed. You can make them up. Excuse me. But the range is just all the outputs that appear. And let's see. I'll go from smallest to largest. We have -7, -3, 1, 3, 17, 18, and 20. Okay, so if your domain and range, your sets of inputs and outputs are finite, you would just list those values and make sure you enclose that list with curly braces. And if there ever is something that repeats in the set of outputs, which is allowed, as long as no input repeats, it's okay to have multiple outputs. You do not need to list that value in the range more than one time. It is okay, even if a value repeats in the range or set of outputs, you really only need to write it down one time. Okay, so example 4. So we just saw if a relation is represented by a table, we saw how to determine whether it was or is not a function. Example 4, I want to know if each relation is a function, but this time the relation is given verbally. So there's like a verbal prescription for how to relate or pair elements together, as opposed to just listing them in a table. Again, in some of the examples following, we will notice that, or we'll be describing functions by equations or expressions. And I'll also be introducing some notation as well. Okay. So now, is the relation a function? If so, it says identify the independent and dependent variables. Okay. Alright, so now remember, if you go back to the definition of a function on the previous page, you will see that it said whenever two quantities are related through a function, you always want to say that the output is a function of the input. So for part A, if you read this, is the price of an airline ticket a function of the length of the flight? Okay, so first thing, if I want to determine if this is a function, it's helpful to know what the inputs are and what the outputs are, which also helps me find independent and dependent variables. So I want you to notice there are two quantities here. The first quantity that we're relating is the price of an airline ticket, and we want to know if that quantity is a function of the length of the flight. Okay, so there's two quantities, they're related together. Is the price of an airline ticket a function of the length of the corresponding flight? Now remember I said output, if there is a function involved, the output is a function of the input. Okay, so in this particular example, the length of the flight would be the input. Right, so for a particular flight, or, well, actually you would just pick a number, like say an hour and 30 minutes. Okay, so those would be your inputs, would be the lengths of flights. And for an hour and 30 minute flight, okay, you're going to think if that single time is going to correspond to a single price of an airline ticket, or does the length of a flight not necessarily correspond to a single price? Now, in this particular example, there are a lot of different reasons why this is not a function. You're going to want to say no here, and that's because for a particular flight length, there are multiple airline prices. There are more than one way to see this. One way to see this is a lot of planes have first class and I forget what standard is called, but we'll just say first class and standard seating. And of course, the flight would be the same length, okay, but you're going to end up with two different ticket prices, right? You're going to have a ticket price for first class, and then you're going to have a ticket price for standard seating. So you would say no. It is possible that the length, or let me phrase it this way. Let's just say that flights of the same length okay, so that length would be a single input. Okay, so flights of the same length can have different prices. So again, an hour and a half flight. Again, you can think of it, there's the price for standard seating, and then there's the price for first class. Okay, so that would be a single time that has multiple outputs, i.e. different prices. Another way to think of it is you might even have two flights to two different destinations. But if they have the same length, that would represent the same input, and two different prices to two different destinations, or two different flights to two different destinations, could have different prices for their tickets. Okay, so again, that would be another example of one input having multiple outputs. If you look at part B, here's another function described verbally. Is the social security number of everybody in our class a function of the name of each student? Now again, there's two different sets going on here, two different quantities. Your inputs and outputs don't necessarily have to be quantities. They could be any collection of objects, collection of colors, all sorts of things. Okay, but is the social security number of everybody in the class a function of the name of each student in this class? Okay, so again, it says that if you're going to relate to quantities, the output is a function of the input. Okay, and so you have to make sure that each input gets assigned only one output. Well, assuming none of you have the same name, which you don't, since each of your names are the inputs, this function assigns to each of your name your social security number. So yes, this is going to be a function since each student has only one social security number. Okay, yes, it's a function. Each student, or which is each element of the set of inputs, only has one social security number. Each input gets assigned only one output. This relationship is a function. Okay, so we've seen how to describe functions through tables, and we've also seen how to describe functions verbally. Section 1.2 is going to focus more on graphs to determine if graphs represent functions or not. And we are going to see in just a second functions that are given by expressions or equations. First, though, before I get there, I want to talk about function notation. I'm going to talk about the idea of how a function works. So, it says, function notation, you're going to let x be an element of the domain of a function f. Really, all that's saying is that x is going to be the variable that represents inputs. Okay, so that's going to be the independent variable. And if you look here, all functions, if some relationship represents a function, you would typically pick some letter to represent that function. And the general letter to use is F for function. Okay, so x is going to be the variable that represents numbers in the domain, okay, associated with the independent variable. Then you use the notation f parentheses x, which we read as f of x. That's just going to denote the output corresponding to the input value of x. And then you often assign another variable, y, which is going to be the dependent variable, represents an output. You assign that to f of x and write y equals f of x. Okay, so when you write this, y equals f of x, and actually let me do one thing. That was the name of the function right there. So y equals f of, and I'm going to use blue for x here. And I'm actually going to switch one little thing. Okay. So why am I doing this? Well, I just want to point out that anytime you look at a function, holy cow, we don't want that much. Excuse me. Okay. So inside these parentheses, you're going to write down x. That represents the input. And then I'll explain this notation a little better in a second. Okay, but outside the parentheses, f, this is just the name of the function. Now for us, when you plug x into f, that's what this f of x thing is, whatever the function is supposed to do, it's going to give you an output y. So f, this f right here, this f just changes an input value to an output value. Okay, and you can think of it like this. You can think of it as a picture. Okay, so over here I have the set of inputs. Over here on the right I'm going to have my set of outputs. Okay, so this could be just called the domain and the range if you like. And in the middle, in the middle I have a function f. And you can think of this as sort of a machine, if you will. Sorry, it's hard to write. Okay, so you can think of a function as a machine. It's something that you put something into the machine and it changes the value. Okay, or it tells you how to relate the input value to the output value. So now what this means up here is you're going to select an x value in the set of inputs. Okay, again, that's just x just represents an arbitrary input. That's why it's called a variable, because it changes. And since it corresponds to the inputs, it's the independent variable. Now what you're going to do is you're going to run that value through the machine. And the machine usually is going to be an equation. Right? So you'd plug that x value into some equation. And what's going to happen is f is going to spit that out of it's going to go through the machine, and it's going to land in the set of outputs. And that value is going to be called f of x. Okay, you can think of it this way. X has been plugged into the machine to get my output y. Okay, so a function is really just like a machine. It changes inputs into outputs. This way to convert inputs and outputs can be described verbally. Again, you can write it down in a table. You can just list it. You can use a graph to describe functions, and you can certainly use equations or expressions, which we'll see in just a moment. Okay, so there's the notation. Now I can talk really quick about arguments, and this is going to be more important probably later on when I talk about logarithmic functions. But I can certainly briefly talk about arguments right now. Okay, so it says the argument of a function is the expression on which the function works. Okay, so we're going to see this in a second. I might want to show you just a quick example. Let me actually write down an equation. So f of x equals, excuse me, f of x equals, even if I do something like 3x plus 2. And just a quick example of what this means. So this formula right here, this is kind of the recipe for how to cook up or make the outputs from the inputs. it says whatever your x value is on the left, so f of x, whatever your input is, you're supposed to multiply it by 3, and then after multiplying, add 2. For instance, if I want to do f of 2, I would do 3 times the input 2 and add 2. So notice the input showed up on both the left and the right. If I want to do f of minus 1, that would be 3 times minus 1 plus 2. Again, notice the input on the left and the right. Okay, now in these first two examples, the arguments are really just the inputs -1 and 2. Okay, that's the expression on which the function is working. Right, on the left side, this is just using x as the argument. Okay. And of course, I could have calculated these. The first one ends up being 6 plus 2, which is 8. The next one is -3 plus 2, which ends up being -1. Okay. Now, you might have something like this. Again, I'm going to use f of x equals 3x plus 2. But I might look at the expression f of 2x plus 4. So I want to stop you. Again, I can do a particular input like f of 3. Okay, that says, okay, the function says you take 3 times the input, add 2. So notice again, x is replaced on both sides by 3. You get 9 plus 2, which is 11. Now this time, 2x plus 4 is the argument. So basically, the argument is what is ever inside these parentheses. Now this is a little bit different this time. Now my input or my argument is 2x plus 4. Okay, it's not 3 anymore, like it was in the previous example, but the same rule would apply. Right? This function is always 3 times whatever the input is plus 2. Okay? And this always goes in for the x over here. So this would also be 2x plus 4. Again, if I want to do, even if I want to change variables, I can do f of w, which would be 3 times the input of w plus 2. Okay, and again, I'll do one more weird one. If f of x is 3x plus 2, I could even do a quadratic expression, x squared minus 2x. Okay, and again, the idea is whatever the input is, that value gets multiplied by 3, and then I add 2. So it's 3 times the input plus 2, and then you're just going to take this whole x squared minus 2x and plug it in there. So it ends up being 3 times x squared minus 2x plus 2. Okay, and again, this time, x squared minus 2x, this is the argument. And again, I'll use that terminology on and off. When it's more relevant, I'll use it. I probably won't use it very often until we get to chapter 3. Okay, and then of course, from there you'd have to simplify this stuff, but we'll see that in the next example. Okay, algebraic representations and algebraic notation. Okay, so again, I've shown you functions given both verbally and with a table. We now describe functions using an algebraic equation, which I did a little bit up in the previous example. Okay, so now I want to do some calculating outputs from inputs. Now, if the function g of x is 4 minus 3x, and I say I want to find the output that corresponds to the input of 2. So now g is the name of the function. This means that I'm plugging in 2. And what is the function supposed to do? It looks like up here you're supposed to multiply x by -3 and then add 4. So one thing I could do is, well, I guess just looking up there, I can just do 4 minus 3 times whatever the value of x was, which this time is 2. That gives me 4 minus 6, which ends up being -2. Okay. Now a couple things. That's saying that for this particular function, when the input is 2, the output is negative 2. You are going to see that later on when we start talking about graphing a function. Basically, a graph of a function is just describing all inputs and outputs simultaneously or at the same time. This would mean that the point 2 comma minus 2 is on the graph of g, right? This is x and this is g of x. Okay, so the output is always the y coordinate. So I plug 2 into this function, I get negative 2 as an output. That would give me the point 2 comma minus 2 on the graph of g. And I'll talk about graphing points later. Okay, so next. Now I want to do g of negative 3. G of negative 3 would be 4 minus 3 times negative 3. Again, notice whatever is in the parentheses, whatever's being inputted into g replaces x in the equation. Now PEMDAS says, okay, I don't know how many of you know about PEMDAS, and I would make use of this as much as you can throughout the quarter. Using PEMDAS in this direction for the acronym is for simplifying. And then if you use PEMDAS in the reverse order, this is for solving. Okay, so basically we're simplifying in this case. So first of all, you do anything inside parentheses. Well, the only thing inside parentheses, negative 3, you can't simplify that. The next would be to exponentiate. I don't see any exponents. The next step would be to multiply. So I would do the negative 3 times negative 3, and this would end up becoming 4 plus 9. Multiplication done. There's no division. Now you do the addition and subtraction, which when I add 4 and 9 together, I'm just going to get 13. So when the input's negative 3, the output is 13. That would also give me a corresponding point on the graph. Okay. Now you can start doing what are called varied inputs. So if I want to do g of negative 2w, that negative 2w is just going to go where x used to be. So this will be 4 minus 3 times negative 2w. And again, PEMDAS says we multiply first, so 4 stays out front. Negative 3 times negative 2w would give us a plus 6w. Okay, and then one term is a constant term of 4. The other term is a first degree term. That means you have w to the first power. That is as simplified as you can get. There's no like terms to combine, so I just get 4 plus 6w. Okay. Now finally the last one, this is going to come up in the next example as well. If I want to do g of x plus h is the argument, and the function, and the way the function works is you're going to take that input, multiply by negative 3, and then add 4. Okay, or just x plus h is going to go where x used to be. So this is going to be 4 minus 3 times x plus h. Now you're going to have to multiply first, which comes down to distributing the negative 3. This would be 4 minus 3x minus 3h. And again, that's as simple as you can write it because there are no like terms to combine. Okay. So the next thing I want to do is the difference quotient. This is an important quantity that shows up in calculus. So if any of you are planning to take calculus or business calculus at some point, you will work with this expression quite often. Okay. And I'll have to explain this in another section when we talk about graphs, or we'll probably be talking about average rate of change in 1.3 when we're learning about linear functions, and I will talk about a graphical interpretation of the difference quotient. So right now we're just going to work with it algebraically. h just represents some positive quantity or some non-zero quantity. And what we're going to do is we're going to calculate or we're going to find and simplify this expression when I know that the function is 2x squared plus 1. Okay, so first of all I'm going to write these three things down. Or maybe I'll just do f of x plus h. Okay, oops. So what is f of x plus h? Again, you're going to take the argument or the input of x plus h, and that's going to get plugged in or replaced. You're going to replace x with that quantity. So f of x plus h would be 2. So notice what the function f does. It first takes the input of x plus h and squares it. I probably could have done that before even throwing my 2 out front. So notice, again, look at the function itself. F of x, the rules are whatever the input x is, you square it, multiply by 2, and add 1. Now that the input or argument is x plus h, we're going to square that quantity, multiply by 2, and then add 1. Okay? And of course, f of x, we already know that quantity is 2x squared plus 1. And, well, h is just some quantity. So you really only have to replace the function notation when you're simplifying this. You have to replace the f of x plus h, and you have to replace the f of x, and then you're going to simplify. So now if I'm doing this all at once, if I'm going to find and simplify the difference quotient, okay, this expression is going to equal, I can use a string of equalities for this. Now the first part is what is the f of x plus h. So I'm going to write that down. We just saw that that is obtained by squaring x plus h first, multiplying by 2, and then adding 1. Now I'm supposed to subtract the original function, f of x. Oops, let me erase that and rewrite it. 2x squared plus 1. Now I have to put that in parentheses because it has more than one term. Okay, so now notice I've boxed f of x plus h on the left. That became the 2 times x plus h squared plus 1. I will also be boxing, okay, let me use red. The f of x part was replaced by 2x squared plus 1. And then the h just actually hangs out and doesn't really do anything until for now. Eventually we're going to simplify that part of the expression. Okay, now what does this equal? So now you're going to start working on simplifying this. Okay, so first thing I'm going to do is I'm going to square the x plus h up here. Okay, so make sure you remember when you square something, it's really multiplying it by itself. We're going to have to FOIL that. And then looking at the first step, I'm going to distribute the negative to give me a minus 2x squared and a minus 1. Okay, now in the next step, I will multiply the x plus h's together. I'm going to multiply these two, and you have to FOIL it. It ends up being x squared plus, now you're going to get an xh and another xh when you do the inner and outer multiplications. So it becomes x squared plus 2xh plus h squared. And if you actually look up here, you're going to notice that the plus 1 and minus 1 are going to cancel. I'm just left with a minus 2x squared. Okay. Now I'm kind of out of room. The next thing I'm going to do is distribute this 2 through. I'm actually just going to erase this part and just write the result up here. So this is going to end up being 2x squared plus 4xh plus 2h squared, and then I still have the minus 2x squared. Okay, so I just distributed the 2, I'm still dividing everything by h. Now you'll notice you'll get another piece of cancellation. You'll have a positive 2x squared and a minus 2x squared. So the only thing left would be 4xh plus 2h squared all over h. Now, whenever you do these difference quotients, whether it's a linear function, a quadratic function, whether it's a quotient or it has square roots, you're not done until you cancel this h in the bottom. And after all the expanding and simplifying and canceling, at this step you should be able to, like in this part, you should be able to factor an h out of the numerator. So notice both terms in the numerator have an h. There's an h in the first term and an h squared in the second term. You're going to factor that out. Now since you have multiplication left over, the h on top and the bottom will cancel. And your final answer, oops, there's a mistake. Your final answer is going to be 4x plus 2h. Once you cancel that h, you are basically done. So there's the difference quotient, 4x plus 2h, fully simplified. If we need to do more examples, we can do those in our Zoom sessions. Certainly make sure that you practice those. There will probably be, you can probably bet on there being a difference quotient question on the exam. Okay. Now lastly, we can talk about domains. Okay. Now it says the natural domain of a function, when a function is given without reference to a specific domain, so that means like someone just gives you a function, it doesn't necessarily represent a context, like it's not an application problem or a word problem. The natural domain, or sometimes just the domain, is understood to be the set of all real numbers for which the outputs of the function are also real numbers. Okay. It says write the domain in both interval and set notation. On your online homework, it's typically going to always be giving the domain in interval notation, but I will accept set notation on exams. Okay. So the first function, 4 minus 3x, turns out that this is what's called a linear function. Oops. Okay, the first function here, we're trying to find the domain and range. The first is called a linear function. We're going to learn about these in section 1.3. Okay. They're called linear because their graphs are lines. Now if I want to find the domain of this, you're asking yourself, what real numbers can I plug in to the expression 4 minus 3x to make sure that I get out a well-defined real number? The only times you are going to have to you'll have to omit values from the domain is if your function includes fractions or quotients or radicals, like even square roots, fourth roots, sixth roots, etc. This function in interval notation, okay, the domain ends up being all real numbers because 4 minus 3x will always be a real number for any real number x. So the domain here would be, in interval notation, you're going to write minus infinity to infinity. So this is what I'm calling interval notation. That's how you write the set of all real numbers. Okay, or you can write the set of, this is the set notation now. The braces stand for set. It's a set of all x. The colon stands for such that. So it's a set of all x such that x is a real number. Okay, so that's again this is called the set notation. Okay, so there's, on the one hand, all real numbers in interval notation, which is written as minus infinity to infinity using parentheses, or you can say the set of all x, so that x is a real number. Okay. I like to keep my videos around the 50-minute mark, so I apologize for getting over that, but I'm almost done here. Okay, the second function, g of x, involves a square root. Okay, now you might recall that you can only take the square root of 0 or positive numbers. Okay, so right away there's a restriction. If you look at what's underneath the square root, x minus 2, okay, any number underneath the square root has to be greater than or equal to 0. We'll talk about solving inequalities later, but you can add 2 to both sides, which tells you that x would be greater than or equal to 2. And again, 2 ways to write the domain. One is in interval notation. You can write bracket 2 to infinity, and then the bracket means that 2 is included, and this represents the set of all numbers that are 2 or bigger. Okay, and again, this is the interval notation. Okay, another way to write the domain is in set notation, as the set of all x such that x is greater than or equal to 2. Okay, notice that you would not be able to plug, say, 1 into this function. I would say something like g of 1, that's the square root of 1 minus 2, that's the square root of negative 1, okay, which is not a real number. So that means that g of 1 is undefined. Okay, or 1 is not in the domain. Okay. Okay. So now, if I want to find the domain of, say, h of w, so w is the letter representing the independent variable, h is the name of the function. In this function, the rule for this function, again, the independent variable is represented by w, the function's name is h, and this function takes the cube root of the inputs w. Okay, so this time, the domain is the set of all numbers that you can plug in this function, the set of all w's, so that the cube root of w is a real number. Now, since you're taking a cube root or a third root, since that is an odd root, you're actually allowed to take an odd root of positive numbers, negative numbers, and 0. So this time the domain would again be all real numbers, or again you can write that as the set of all x such that x is a real number, or some people simply like to write a script r, so that also represents the set of all real numbers. Okay, and then finally, last problem, and we'll call it a day. M of z is 1 over z squared minus 2z minus 24. Okay, now this time it's a fraction, and you want to make sure that the denominator is not 0. So you can plug anything you want into this function, but since the output is a quotient, z squared minus 2z, whatever the input is, whatever z you choose, z squared minus 2z minus 24 can not equal 0. Now you will notice this will factor as, I think, minus 6, z minus 6, and z plus 4. And you want that to not be equal 0. The only way that can be 0 is if z was 6, so z cannot be 6, and z cannot be negative 4. Okay, so you can plug anything you want into the function m as long as the input z is not one of those two values because they make the denominator 0. Now, there's two ways you can write the domain. I didn't leave myself much room, but let's see if I can fit this in. The interval notation, you would have to write, well, actually, you know what? Let me draw a number line first here. You might be able to visualize the domain. So here's a number line. This represents the x-axis. Here's -4. Here's 6. And I want you to notice you have to avoid those numbers. So I draw open circles to represent holes. And then x can be anything but where those open circles are. And you'll notice that this has broken up the domain into three parts. There's the part that represents numbers from -infinity up to -4. Parentheses means do not include. There's the numbers between -4 and 6. Parentheses means don't include those numbers. And then there's also the last set from 6 to infinity. So that's the interval notation for the domain. You'll notice that the set notation is much easier. It's a set of all x such that x... Sorry, it's not the set of all x. My bad. This should have been the z-axis. This is the set of all z such that z does not equal 6 or -4. Okay, so much easier to write the set notation when you're avoiding specific numbers. Make sure to look at the book. Do as much practice as you want. You can Google videos finding domains of functions, algebraic functions. There's tons of videos. You can read through examples in the book. Send me an email. Call me at my Google Voice number. We can do a quick Zoom meeting and screen share with each other. Again, I'm going to try and keep the videos around 50 minutes. This one's 57 right now. If you have any questions, let me know. Thanks for tuning in. Have a good rest of your day.